Well, I think we can get started for the OpenFAST workshop. Yeah, if everyone wants to come forward, that would be great because it's a big room. Hey, man, no worries, Manuel. And materials, if you want to access all the presentations and the sample simulations that Emmanuel will go through, everything is at that tiny URL. If you're online, you can just access all that and you're good to go. If you don't know me, I'm Jason Youngman from NREL. I've been using OpenFAST, developing OpenFAST for over 20 years. And my partner in crime today is Emmanuel Brandlard, who just walked in from University of Massachusetts. He's a professor there. He used to work with us at NREL, and we're still working together now through some contract work. So the way this is going to work today, we're going to have 3 2-hour sessions. So the first one now is more providing the background about OpenFAST and how it's used. Bit of an overview. We'll have lunch break at 12, and then Emmanuel will take over at 1 o'clock, and we'll do more of the hands-on, how to actually run OpenFAST and all the, and I'll propose some challenges for you to work through if you have time this week to learn more. After that, at 3 o'clock, I'll do a final wrap up of what we haven't covered already. And then we'll end at 5 today. I'm sure Emmanuel and I are here all week. We actually also put together an OpenFAST office hour on Friday, I think right after lunch at the conference. So if you have questions on the challenges that Emmanuel is going to pose to you, have time this week to work on it, please come by and ask those questions, or you just want to talk about OpenFAST, geek out a bit, we're happy to do that too. That's a completely open-ended office hour. So nothing there for at 1 o'clock on Friday, but please join us if you're interested in that. Again, workshop materials there at a tiny URL if you want to download everything. And then let's see. Can you guys all hear me? This room is like huge. So it's a little dead. But let's start by just going around and saying hello. And so, yeah, if you want to give me your name, where you're from, and then your relative experience with OpenFAST or wind turbine simulation in general. Like, are you at the level where you could teach this class and you're just here for fun? Are you like brand new, don't know anything, or are you somewhere in the middle? I'd love to just know that, so we can tailor the material appropriately. So I'm Jason. Obviously, I'm from NREL and I can teach this class, but yeah, let's go around.
Manuel brand new, and I've been developing OpenFAST for the last 6 years.
I'll just go down the rows here. Yeah.
Okay. My name is I am Joel Kim from Institute for Advanced Engineering, South Korea. And I'm here for the meeting at option, and I want to use so that's for South Korea.
Thank you.
My name is Peter Schmidt. I'm from UMass.
Great.
My name is lecturer at the University of
Great. You black.
Well, I'm from I yeah, so I have my own kids, I'm adults. Things don't get a lot of personally. I'm from the
I'm a professor at the University of Florence, in Italy. The group uses research every day. I did it back in the with the PhD.
I it is Ganesh. Plus, it's new to me, so I worked on larger discipline. It's really yes, due to emotional. Everyone, I don't think it's a state university.
Excellent. So we got a range of capabilities here, and so we'll try to tailor it to everyone. But yeah, please ask questions as we go forward. And I always like to start by, let's see, is this going to touch the screen? I guess. Yes, introducing some fundamental concepts that, and this will be very interactive, hopefully, that sort of set the stage for what we're going to talk about. So hopefully, maybe call it like a wind turbine 101 basic. So obviously, power curve. Wind is cubic with power. And so normally, very low wind speeds, or just sitting there kind of waiting for the wind to pick up. Once you cut in, you try to maximize the power of the rotor. You follow this cubic relationship up, really trying to get as much as you can. At some point, you hit the rated, say, capacity of your generator, and you just try to maintain power as the wind speeds get higher. And eventually, you shut the machine down and get to more of a survival mode, where you're not really producing power at all. And this happens basically through the standard control options. So in region, is this thing have laser pointed? This is something on the screen, but in region 2, so between cut in and rated, usually you're trying to say, I want to maintain tip speed ratio at my maximum. So you're linearly increasing speed, rotor speed with wind speed. Once you hit rated, you keep the rated speed and use blade pitch to sort of shed load. And cut out, you basically park the blades to feather the blades to 90, just try to ride through the storm going in. So my first question is, if I'm talking about steady wind, so wind is just steady at a fixed wind speed, where's the thrust highest in this on just the rotor? Talking about the rotor, where would thrust be highest? Would it be cut in, rated, cut out, or the 50-year extreme wind speed? Where's the thrust highest in this control, in this turbine, where it's basically a typical optimized controller, where it's optimal, below rated, pitches out, and then feathers to 90. So where's the thrust highest, the mean thrust in steady wind conditions? Anyone? What are the 4 options? Yeah, the back. Nice, are you? Yeah. Rated. Anyone else disagree with that? Do you want to explain why you think it's rated? Right? I don't disagree. So I'll plot what I think it will roughly look like. So usually the thrust follows some sort of quadratic law up to about rated, and then basically comes back down. And then maybe it starts growing again if you get to really high extreme wind speeds. But you're feathered, so hopefully most of that is just drag load on what's left, and maybe some load on the hub or cell or something. So my question, I guess, next is, so thrust is going down. Why do we have to shut down the turbine at high winds? Just let it ride through. Thrust is actually lower. So why do we actually shut down? What's driving that? Anyone? shut down on high winds? Any idea why you do that? Yeah, please. Yeah, it's all about stochastics. It's all about turbulence. And so maybe my next question is, if you look at standard deviation of the wind speed, so fatigue is really what's driving the shutdown. Or turbulence intensity, what do those curves look like? If I go to higher wind speeds, is my standard deviation going up or is it going down? Is my TI going up or TI going down? At least at a typical site. What do those look like? Any ideas? And if you've downloaded the slides, you probably already see it. But let's look at standard deviation. Is that going to go up or down with mean wind speed? Please. Perfect. I completely agree with that answer. So this is at least how the IEC will say the typical site goes. The standard deviation is going to go up of your wind speed, and your TI is going to go down because the TI is like the standard deviation divided by the wind speed, and the denominator is going a little bit faster. And so this is really what's sort of driving. If you look at basically the range of so basically add the standard deviation to that load, it looks something like this. Maybe it's a factor of 2 above the mean for at rated. Of course, it spreads out as your standard deviation is going up. The load's going to get worse, and eventually fatigue is just going to hit you at the high wind speed. So that's why you shut down. Whether the peak now of the load is at rated, cut out, or the 50-year extreme probably depends on the turbine. I kind of drew it way it commonly is, but that gives you some hopefully basis of what you're expecting in the different operations of the turbine. Okay, next sort of fundamental concept. If this is like, you have to understand this or you can't get anywhere. So mass spring damper system. I have a mass M, spring K, dash spot C, and have applied force F. Equation of motion. What's the equation of motion for this guy? In terms of those variables. Anyone? Equation of motion for that system? Trying to get it interactive, so please talk. Yeah, you and you get your name, but yeah, sure. Yeah, it's one. Yeah. Yes. Perfect. I think that's what you said. And so I could think of this as a very simplified turbine, right? Maybe that's my tower mode, and the cell has big mass. They have the rotor on top, and I have some spring damper representing the tower. And so there's the equation of motion. And so now my question for this system, very simple system. I think you all studied it in, certainly in undergrad. What's the difference in this system between a resonance and instability? So how would I make this system in resonance, and how would I make that system unstable? First of all, resonance. What would sort of drive that system in resonance? What does that look like? There's some characterization of that system to make a resonance. What would that be? I'll try again.
Like the force you
So I take my force and I say that's some cosine or sine, say of omega. And if that omega lands right on the natural frequency, that square root of k over m you mentioned, I can get resonance. And the thing with resonance is that basically grows linearly. It depends on damping, but it will grow linearly. So that's bad. Not terrible, because hopefully you realize that sort of shift away, but it's bad. Now, what would instability look like? How can I make that mass spring damper system unstable? What? Light group. Yes, you change a sign. Typically, it's in the damping. So great, I agree. So if I take my damping, I say, well, that's a negative. That's a negative value. What you really get is an exponential growth. So it's not linear anymore. Now it's exponential. And eventually, that's either going to destroy the system altogether, it's going to blow up, or maybe you'll hit some nonlinear limit cycle oscillation. But that's bad. And so a big part of loads analysis for wind turbines is about this. What where's my resonance? And that's usually what, is what frequencies of excitation coming at. I don't want to dwell on that for long. So I want to avoid resonance. I absolutely want to avoid instability. So that's really bad. So usually instabilities happen, some aerodynamic interaction. Yeah, that damping can become negative through aerodynamics. So we have to be very careful with those things. Finally, the last sort of fundamental concept I think is really important is that we talk about resonances being bad. So how would you get a resonance in a turbine? What you see is that basically a turbine, of course, operates in a turbulent atmosphere, and the rotor basically samples this turbulence. And if you imagine just a linear shear, my blade's going to cut through that, and that blade's going to feel basically a 1 per rev cycle because of shear. I think of turbulence as like a Fourier series. So I have the linear term, I also have the quadratic term, the cubic term, and so on. And it's really kind of sampling that nasty field. And what that really does is that it samples the turbulence. And so the blade is going to see excitation of that blade at 1p, 2p, 3p, p, and so on, all the harmonics of the RPM. Of course, the energy in that wind sort of decaying with frequency. And so, the lower frequencies may be higher than the higher frequencies, but nevertheless, it's going to sample that. If you take that sort of 3-bladed rotor, you put it on a tower, you're going to see something very different in the tower, or so the drivetrain, the nacelle, the tower. You're going to see basically a sampling of 3p, 6p, 9p, because it's feeling like the effect of the rotor. So these are the frequencies that are extremely important for the blades and the support structure. And of course, as we get to larger and larger turbines, again, remember, omega is proportional to wind speed. Usually trying to maintain a tip-speed ratio. And so normally for larger turbines, these frequencies are all getting lower. So lower and lower frequencies become more important as you get larger turbines. So again, that's where the resonance is going to happen usually, is some harmonic of the rotor speed. So any questions on that? That's sort of fundamental concepts, and we'll use them all. I think all those sort of things throughout the day, but fundamental things. Any questions on that? Makes sense. Hopefully it's not too new. Okay. You want to say something? Please.
I was just going to say, in your case, the force was only a function of time, right? And was it the function of Q and Q dots?
Yes.
Without stability.
Yes, definitely.
The force comes from the wind, it can be unstable as well.
Yeah, so very much that's true in their elastic sense, right? Because the aerodynamic force is not just a function of time; it's going to depend on the motion, both displacement and velocity, maybe even acceleration, right? So it's all there. So great point. So that there's some fundamentals of that you need to understand for wind. Next thing, design principles of wind. Maybe just jump through this here. So really, I think it's this coupling that really drives loads analysis for wind turbines. So of course, we got the aerodynamic load that hits the rotor. As Emmanuel was saying, it's an interactive effect between the rotor and the wind. There's structural analysis. So these things are large and flexible. Most of these systems now are the size of buildings, skyscrapers. So these are, there's lots of modes that can get excited. Those natural frequencies, not just one. In the case of mass spring damper systems, there's a range of natural frequencies, and you always have to worry about resonance of those things. First, there's a control system there. So there's basically a brain in that turbine reacting to its environment, making decisions based on sensors and doing actuation. Then, of course, the hydrodynamics for offshore systems. We'll talk a bit about all those things. So structural loading is sort of key to design. And if you want to know how the process is laid out, it's really spelled out by things like IEC design standards. This kind of lays out what the IEC, like 61400-1 for land-based, -2 for distributed wind, and -3 for fixed and floating. What they do is they lay out a series of load cases that you have to run. So you basically take OpenFAST, you never just run it once, you always run it through a range of conditions. So operational conditions, say between the cut in and cut out wind speed, where you basically see what it's going to do for all the conditions that we see. Addition to normal operation, there's a bunch of fault cases. So the turbine, loses the grid or something, the blade doesn't react to its control system or something. So there's faults that could drive loading. We have to run those cases. Startup and shutdown events. And of course, during the extreme conditions, the storm conditions coming through, you typically park or idling and you try to ride through the storm. And those things can also have faults. And so the IEC basically lays out what these load cases have to be. And that's what you're trying to do with OpenFAST. And so really trying to usually aim for two things. One is, what's the sort of 50-year extreme load that my terminal will ever see? And I sort of designed for that. The other thing would be fatigue life. Normally designed for say 20 years, maybe it's 30 years, but you're trying to track all the fatigue cycles over its lifetime. And really the tools like OpenFAST sort of fundamental to that. With that, you're trying to basically estimate this load distribution. So what is my sort of, normally say I run my loads analysis, I get what's called the characteristic load, multiply that load by some safety factor, IEC that's called the partial safety factor for loads, and I get my design load, that red curve. So here's my sort of range of design loads I can get. So I run all my cases, and that's sort of my extreme set of loads I get. And I want to make sure that that extreme is less than my strength of my material by some, again, factor, usually a safety factor on strength. And so that's really what we're trying to do for load calculation. And in terms of number of simulations, usually for a land-based turbine, there's about 1,000 cases for a drive design. So you usually run OpenFAST about 1,000 times, say in a design iteration. For offshore, that usually goes up by an order of magnitude, maybe 10,000 cases that are really important. Maybe running more to screen what's important, but those are usually what's designed driving. So it's not just one event that's important. It's lots of different things that can be important. And so normally we do that either through some sort of high performance computer, or I have, big computers that I just throw, run thousands of jobs at once. Or maybe you're doing that through the cloud. Probably rarely you're just running on your personal laptop and running one at a time. Maybe just to play with things. But as you get to really be a big user of OpenFAST, you'll be doing this on an HPC or the cloud. And then in terms of response, again, the ultimate loads, we're talking, as we sort of imply by the fundamentals there, it's not necessarily driven by the highest wind. It could be, but it doesn't have to be. Maybe it's some gust that rated that drives your ultimate load, your highest load your turbine will ever see. So yeah, be careful about that. For fatigue, it's really about trying to track cycles over all the lifetime, all the conditions it can operate in. And then, of course, the two things we also mentioned, resonance. You want to avoid resonance, at least mitigate it as much as possible. Your turbine has variable speed, so it is going to go through resonance at certain points in its life. But you don't want to dwell on that for too long. And of course, instability, you want to avoid that at all costs. You don't want the model to be unstable. And so these are all sort of key things in response. Yes, if you were here at the previous thing by Misha, he showed various ways of showing the NREL tools, and this just is just my way of sharing that. So this kind of shows fidelity across the columns and single turbine and full wind farm as the rows. And so OpenFAST there sits in the middle. That's what we're mostly going to be talking about today. If you want to curious about the rest of the tools that NREL has, we have basically low fidelity models. Wisdom has a set of low fidelity, basically quasi-static or frequency domain type models in it that can do a turbine, but in a much more lower fidelity. And of course, you want to move very high fidelity, usually on the aero or the hydro. Say I want to replace my engineering model with a CFD type solution, you move to like SILFA or Excellent. Likewise, for the full plant, I think there's a Flores workshop happening right now. That's basically steady state aerodynamic performance of wind farm. If you want to look at the dynamics of the wind farm, you use Fast Farm or WindSE, and I'll talk a bit about Fast Farm today, not too much. We should really have a separate workshop on that. And then, of course, you can use the high fidelity in that space as well. I like to say that these things are not, they're very interactive. I've used a lot of high fidelity to basically inform the engineering models. Either you're validating or you're calibrating something from a high fidelity simulation. So you're almost never running just high fidelity. You're usually doing it in conjunction, say, with OpenFAST. Sometimes we do that to calibrate and improve the model. Sometimes we just say, well, I don't know. I don't really understand the physics that I see in the high fidelity, and I just want to replace it with some reduced order, surrogate model. We're seeing more and more of that show up in AI and ML coming down the pipeline. I think the other way, it's also complementary. So I think usually with high fidelity, you can only run a few simulations for a given project. I think the most I've ever ran in a given project is 10. whereas in the OpenFAST run 100,000s of times. And so I think there's also complementary there where we can really kind of quantify uncertainty with engineering models that you can't really do on the filling side. So they're very complementary activities, but today we're going to focus on OpenFAST, and of course the connections will hopefully become clear as you go forward. And in terms of how these tools are used, of course, because it's an engineering model, we're not resolving everything directly. So there's obviously fundamental theory, like, F equals MA is certainly in there, but we've made some fine assumptions at some points. We're not fully resolving Navier-Stokes equations, say for fluids. Engineering model is also based on whatever technology you're focused on. So if you have some new, say, partial span pitch design, you want to look at that, design around it. You have to bring the physics of that system into OpenFAST. And a lot of OpenFAST development sort of, I want to target that. We haven't done that yet. As I mentioned, using a lot of computational solutions or experimental measurements to sort of validate or calibrate your model is important. And then once you have the model built, the applications are endless in terms of designing new turbines, how new sensors will interact with the system, looking not just at the turbine level, but at the farm level, how things interact with the farm, and of course, all the offshore structures and new technologies coming down the pipeline. So hopefully that's a very broad brush of where the tools are used. Any questions on that background? I have various pause points because it's best to take a water break. But yeah, please ask questions if you have any. I know this room is like large and makes it a little dense. Please raise your hand, ask questions. Talk a bit about an overview of what we'll get through. So first of all, of course, OpenFAST, really about full turbine aeroelastic calculations. Also, land-based turbines, offshore turbines, fixed floating. If you're into underwater turbines, MHK, we also have capability for that. I would say there's two ways to run OpenFAST, and Emmanuel will get into the details, but one is just running time domain simulation. You set up your input file, you run the case, you get the outputs. The other one is linearization. We'll talk briefly about that as well. So you can pause the model basically at any point in time. It's a nonlinear model. Basically extract all these Jacobians out of it. Say what's the relationship between my states and my input, or my states and my states. Linearization is like extremely cool. Like it's a nonlinear model, but if you can linearize it, you can really understand it. Because all these sort of theories out there for linear systems, you can, of course, compute natural frequencies, mode shapes, damping ratios, all from the linear model. You can, do controls design, a lot of controls theories based on linear models, and a lot of instabilities. You can look at the damping matrix directly and say, well, C negative, is that bad? That can happen with linear models. You can do that on the mobile fast. And in terms of modules, OpenFAST, we will go through all these. So this shows the high level. I should have mentioned at the previous slide. In terms of these slides, anything that's not marked is basically available now. 3.5 or 3.5.4, I think is the current release. I do mark, what's coming in 4.0 and 5.0. Some things are coming out very soon, so I star those here in the presentation. 4.0, I was really hoping it would be out this week, and I would have updated the slides for that. But 4.0 is like this conference. I hope to see the email this week saying 4.0 is coming, but if not, by the and then 5.0 is also coming very quickly. A lot of things are sort of coming through. 4.0 has been this bottleneck for a while, but anyways, 5.0 is going to come by the end of the year. At least that's what I've been promised. So, anyways, I'll mark things. So in this case, C state there is bulleted. So if you're familiar with this, that Hydrodyne had C state sort of built into it for a long time. We never called it C state directly. 4.0, you'll see it as a distinct module. It's called C state. And we'll explain more of that going forward. I know I've already been asked, like, is this going to focus on fast farm? And we really should have a separate workshop on that. My hope is that if you can understand all these sort of principles of OpenFAST, fast farm is like just one step above that. I think the hardest part about fast farm is setting it up. So like the model is a little harder to set up. But if you can understand the concept of OpenFAST and know how to run that, you can learn how to do fast farm. So like it's just one step in complexity, and there's a lot of Python scripts that allow us to run that well. But if you don't know what any of that is, what happened there? Sure that. Basically, we have each now wind turbine in your wind farm is an OpenFAST model. And so this turbine, this wind farm has 36, and I can show that animation. And if I click on it, I guess. This is actually a fast farm that's not large eddy simulation. This is a fast farm simulation. There's 36 turbines there of this King Plains wind farm. So each one of those turbines is an OpenFAST model doing its thing. And now basically what fast farm does is it does all the wake part of that calculation. So of course, OpenFAST will calculate the wake of an individual turbine. This will track that wake as it goes downstream and make sure that interacts with all the other wakes in the wind farm. So that wakes in one turbine can hit the next turbine and have that interaction. That's what we're trying to do in fast farm. So it is still efficient. So on this laptop, usually what we say is one turbine per core. So this laptop here, say, has 4 cores with 8 virtual cores. And so I can run like an 8 turbine farm reasonably on this laptop. But if you want to run, 36 turbines, it helps to have a nice HPC to do that for you. So at NREL, I think we have, nice nodes with 122 cores, I think. And so I can run big wind farms and that sort of the supercomputer. That's the idea with fast farm. You're running it based on one node. So if you want to run, again, 100,000 fast farm cases, you can do that. It takes a little bit of effort, but that's really what fast farm is for. So trying to do the idea of big wind farm simulations, but efficiently. Okay, so let's see. And then this is just mostly lists all the modules. We won't talk about every single module today. We'll talk about a lot of them. That thing out of the way there. So some of them you can see SARD coming in 4.0. So we'll talk about the main things for wind turbines: Elastodyne, Beamdyne, Aerodyne, Inflowind, Servodyne. A lot of the modules, probably 10 of them, half of them are for offshore things. We'll talk about hydrodynamics, the sea state, structural dynamics, the mooring system of a floating system. There's modules for ice loading and so on. In terms of new things coming down the pipeline, let's see, simplify Elastodyne. That's trying to say, if I just want, we often use this in fast farm to say, if I'm running 100 turbines and I only care about loads on a few of them, I nevertheless want to represent the wakes of each one. I have a simplified Elastodyne to do that for me. Basically makes that part go really fast. Same thing with Aerodist. It's like, I don't want to solve whole BEM. I just want to say, here's a thrust curve on that turbine. That's what Aerodist is for. So it's really for making fast farm better. SoilDyne is coming in 4.0 that allows the full soil structure interaction capability through things like UI curves or stiffness and damp matrices. And of course, as mentioned, sea state's been extracted out of OpenFAST and separated out into its own module. Very modular. We'll talk a lot about modularization, and I'll say this a couple times, but I think we're trying to say it's open source and freely available, but we're trying to make it more interactive, where it's not just NREL or UMass giving code improvement out. Really want to say, if you guys have great ideas, say in your PhD project or your postdoc or your postdocs or a company here, we want to say, we're willing to accept your contribution to the OpenFAST community. And we've laid out a process on GitHub. Talk a bit about the code at the end. But please, I think if you're planning to make a code change, just reach out to us. We'll have a conversation. We'll get you set up in the right direction. And we'd love to have that. There's definitely been some key features of OpenFAST that have been developed outside of NREL. And so that's we're really trying to make that community. I think that's what sort of sets us apart from all the other Elastic tools out there. Okay. Now, in terms of the process, of course, OpenFAST, I think, sits in the middle of a bigger process that you're doing. Normally, you say, well, there's lots of inputs I need to define to run OpenFAST. Example for the, one of the big inputs is airfoil data, lift and drag, say versus angle of attack. Usually what you do is you have some sort of 2D airfoil data set, say from wind tunnel or Xflow or something like that. And we have a tool called Airfoil Prep that basically takes that 2D data and does, say, rotational augmentation to that to give you the 3D coefficients or the full angle of attack range that you need for OpenFAST. So that's usually a pre-process that we would use to generate the airfoil data. Sometimes we just give you that. And if we generate a new model from scratch, that would be the process you would use. Another big input to OpenFAST, of course, is the inflow that you're going to run. Whether it's steady conditions, you can just say, here's the wind I want to run. But if we're talking about full field turbulence, some gusts or spectra, coherence, and so on, you usually use a tool. You can use TurpSim is the tool NREL provides. If you want to use the MON model, which is popular as well, alternative to TurpSim, DTU has a free open source code called IEC Turbulence Simulator. Basically does the same thing as TurpSim, but with the MON model. Either way, you can use that inside of OpenFAST. In terms of the controller, of course, that's a lesser controls expert. Controller may be the sort of the hardest part of the elastic solve. NREL's trying to make it quite a bit easy through Roscoe. Basically, with a few basic setup parameters, you can basically get a solid baseline controller for a new turbine. We provide, of course, Roscoe controllers for all our reference models. But if you have a new turbine, you can always start with Roscoe. And I think usually industry has controllers that are one step above Roscoe. Never tell us what they are because that's most like the secret sauce that's in the industry. But nevertheless, Roscoe is a solid baseline to begin. If you have your own, if you're an industry member, you have your own controller, you can plug it fast as well. Another big input is the beam property. So OpenFAST, beamdyne or elastodyne or subdyne will treat the structural members as beams. And so we're not doing solids or shells in the elastic solve. And so how do you get the beam properties? If it's it's metal and it's a circle, I can calculate that analytically. But if it's a composite cross section, what is the effective beam of that? And so we have tools like OMBA4 or PyNumad that are basically that sort of pre-processing engine. Look at the composite layup generates the beam properties for you. Another input, if you're running, say, elastodyne, is you need mode shapes as input. We'll talk about why that is, but two codes shown there for mode shapes. One is B modes, that's an NREL tool. Frame3D, that's not an NREL tool, but we developed a Python wrapper for that, really making the modal analysis easy to give you inputs into OpenFAST. In terms of post-processing, and Emmanuel will cover this more, but several sets of outputs to OpenFAST. Of course, one is the time domain response, and I think PyDatView is probably my favorite tool for that. Emmanuel will talk about that a lot. There's some historical tools as well that can do basically batch processing of output data. Another output that you're going to do is linearized models. So again, OpenFAST can basically generate the ABCD state space matrix of your system. And what do you do with that? There's two tools I would say we often use. One is multi-blade coordinate transformation tool that can do things like your mode shape identification and so on. We have developed a new GUI called ACDC. I think Emmanuel will talk about that as well. Really useful to kind of automate the process of generating camel diagrams and does all that process for you. So really, again, that's about generate mode shapes, natural frequencies, damping ratios. Another thing you may want to do is just visualize the output. So animate the response. And usually what we do with OpenFAST is we output what's called VTK files. It's very open source file format for visualization. And ParaView is a nice free open source, not an NREL product, but we use a lot. And you can just import these VTK files into ParaView, and then you can animate the response. So look at the mode shapes, look at the time domain simulation, just look at your configuration if you want to do that. So OpenFAST doesn't have a GUI, but these are ways to sort of get that out of it. Finally, again, you're never running OpenFAST once unless you're just trying things out. You're running it hundreds of thousands of times. So right now we're focusing all our sort of loads analysis type work into WISE. And so we actually are planning a workshop for WISE at next year's NAWEA, so there's a lot more information coming on that. Yeah, it really automates this whole IEC load case process. A lot of people, more experts in OpenFAST have sort of written their own scripts, either Python or MATLAB to do that as well, but WISE is Python based, basically. Yeah, I would say a big part of our work at NREL is not just developing the tools, but ensuring we have some sort of envelope of understanding of where this tool works well, where it doesn't. And so verification validation is a key part of our activity. I'll talk a bit about some of the things we're doing there. Verification, I mean, comparing OpenFAST to some other code that's trying to do something similar or some benchmark problem, that's been well established. Validation, I mean, really comparing to, say, a really high fidelity solution from large data simulation or maybe some experimental data. And again, to me, it's this combination of those things that really is driving clearing technology. Never just doing it by running HFM. You're combining that, say, with an OpenFAST model. Okay, I'll pause there again. Now we'll start diving right into the details of OpenFAST. Any sort of high level questions before we get into that? Still a quiet room? Please. It was removed. That was added back in, I don't know, it was 3.4 or 3.5, but it is available now. Like if you have a subdyne model, it definitely is visualizable in Paradigm. Yeah. Thank you. It was broken for a bit, but it is fixed. Anyone else? Okay. So this next section is really about the framework of OpenFAST. I think that's sort of I emphasize this a lot just because it's key to understand the whole ecosystem of OpenFAST. But it's talking about not to be talking about specific physics of any module, but how they interact. That's sort of what sets OpenFAST apart is its interaction between everything. And so a little background on what we call it coupling taxonomy. Let's say, first of all, this modularization framework is a way to bring the different physics engines of OpenFAST together into one solve. And so it's very rare to have a monolithic model that's multi-physics. You know, if I have fluid and structure solved with the same set of equations, that's pretty rare. Usually you say, well, I have my structural solver doing this, I have my aerodynamic solver doing that, and I want to make sure they work together. And so usually we have a partition model, and those partition models can either be tightly coupled or loosely coupled. And loosely coupled usually means, you know, I have one model take a step, the other one will then take a step afterwards. So I just sequence in some way. And I don't iterate together. I just let them do their thing. But occasionally I'll basically pause and make sure they share information. Tight coupling says, well, I'll do that, but take one extra step. Well, maybe I'll iterate on that. And so if I step this one forward, the next one step forward, I don't quite like what I see, I can go back in time and try it again. So I can learn from my have some interaction there. Sorry, I said that wrong. That's implicit loose coupling. Implicit loose says, you know, I'll have each module take a step, but I'll iterate on that solution. Explicit means I'll just take one step and call it good enough. Tight coupling means instead of having every module sort of have their own way to solve its system, I'll have one integrator that will solve several modules together. That's shown there in the middle. So I started taking the integration out. So it's time integration out and said, I'll do that at the glue code level. And if you're at NAWEA last year, I presented our new tight coupling algorithm for OpenFAST. That's really on the structural features of OpenFAST, so beamdyne, elastodyne, subdyne. That we now have an option in 5.0 where those are tightly coupled. So a loose coupling of those modules is stable, like it's numerically stable. It works to give us a good answer, but it does require small time steps. And their new tight coupling algorithm makes that much more efficient. So again, that's coming to 5.0. I'll explain a bit more at the last section how that's working, but that's coming very soon. Nice thing about this modularization framework is that each module can also be done sort of independently. If I just want to look at aerodynamics, say without any aeroelastic interaction, I can run aerodyne with its own driver, and I can do that with basically any module. So if I just want to focus on one thing and not worry about its interaction, the framework allows us to do that. Usually aerodyne is the one we focus on, sometimes hydrodyne, but you can really do that with any module. If I just want to focus on that, not worry about its interaction. That's what we call these drivers. We have basically a glue code level driver where we couple everything together. We have individual module level drivers. Now how is this framework set up? Think of the modularization framework as sort of blocks where I have the module itself, and inside that module I have the states of the module. What sort of determines what state the model is in, and the parameters. That's like the constants of the model. And then my module is really driven by inputs. So, how's that module being informed by something else outside of it? And the outputs, of course, what are my modules sharing that other modules may want? And usually these are the variables we tend to use. I think in all this work is the inputs we're calling U. The states are really usually maybe 3 or 4 different things that states normally think of like a continuous time state. So that's what we call X. So usually that means there's some X dot, derivative of that. XD is like a discrete time version of that. So, X at n plus 1 equals some function of X at n. E is like a constraint algebraic state. It's needed, but there's not like a differential equation there that drives it. P, of course, is my parameter. Y is what I'm showing my output. So here's a typical form of a module. Again, it could be either some continuous time differential equation. It could be a discrete time update. Constraints being written usually as some algebraic constraint. 0 equals some function z, where I'm trying to use that to solve the little z. And the output usually just say it's an algebraic thing. So given my states and my input, I can figure out what my output is. So that's an algebraic one. So really, see. So for a loose coupling, basically the module will get its inputs, solve, X, the big X there and the big XD and the constraints, and say, advance this from one step to the next. If I'm ever calling called the calc out routine to calculate outputs, is really solving the algebraic equation. Let's see what I missed on that slide. Now, these are just features of the framework, and we'll talk a bit about what each one of those is. So first of all, a little background on what inputs, outputs, these are like typical examples you'll see in OpenFAST. So for arrow, usually I say so my control volume is around the aerodynamics. So I'm saying, well, my structure is not in my control volume, but obviously I want to know what the aerodynamic load on that structure is. So my output will be the aerodynamic load to that structure. Usually the input, as Manuel was saying, is that I can't calculate the aerodynamic force unless I know what the structure is doing. So its motion, displacement, velocity, rate acceleration is an input into that aerodynamic model. Inside that module, it's using lots of things to calculate the outputs. In terms of usually we talk about layout momentum theory is like a algebraic system. It's a nasty algebraic system, but it's effectively what we call a constraint in this framework. We have to solve, say, for the induced velocity or the inflow angle, with some algebraic constraint. There's also generalized dynamic weight models. I guess we call it dynamic bend, where you basically pass that BEM solution through a time filter. And effectively that introduces continuous time states in the model. We also have this HGM unsteady arrow model that's based on a continuous state formulation. Unsteady aerodynamics, Beddoes-Leishman, classic Beddoes-Leishman unsteady arrow model is written in discrete time, which is, easy to time integrate, but not too useful for linearization purposes. So we have that option in there. Then, of course, the parameters of the aerodynamic model, of course, your geometry, your airfoil data, and your inflow. Hydro, very similar. The output would be the hydrodynamic load, the input would be the structural motion. Internally, there could be states, usually it's associated with that convolution term, which we're talking briefly about. And then, of course, the geometry and the coefficients of the model are the parameters. Controller, again, its output would be what it's commanding to do. Here's what the blade pitch is going to do. Here's the torque. Here's the yaw signal or something. And of course, it's getting reaction loads or motions as input. Internally, it may have analog states, may have discrete states in it, and of course, the gains and the limits to control the parameters. For the dynamics, structural dynamics, F equals ma, basically that's trying to solve. And so the states of that model are like displacements and velocities. The inputs would be like the aerodynamic load, the hydrodynamic load, control commands, and it's sort of outputting everything that the other modules need. Reaction loads, motions, and of course, parameters, mass, stiffness, damping, geometry, so on. So hopefully that gives you a sense of what these things look like. And I think we'll also talk about those as we go forward. Coupling dilemma, all these modules interact together. Instead of trying to make that, spaghetti sort of code to say, well, all these modules have things going each way, we try to say, let's streamline all that, and just say each module is sort of in a column, driven by one driver that's doing all these arrows. The glue code is basically handling all the interactions. So it's saying, well, that input has to connect to that output. That output has to connect to this input, and so on. And all those algebraic equations that define that coupling are in this glue code. So how does our glue code work? Again, explaining what we mean by loose and implicit. So currently OpenFAST uses this implicit loose coupling scheme. By loose, we mean, again, every module in OpenFAST has its own solver trying to advance its time step from one to the next. By implicit, we mean there's like this global predictor corrector scheme on the outside, making sure it's converged. But output coupling, so every module has an output and it's sending its input to another module. Some of the module couplings are explicit, meaning the output basically just goes directly as input to something else. Some are implicit, meaning I can't calculate that output until I know my input, and I can't calculate my input until I know my output. So I have some algebraic system I have to solve. This often happens in, say, hydrodynamics. The classic example is added mass effect. I can't calculate my hydrodynamic force, my added mass hydrodynamic force, unless I know my acceleration. And I can't calculate my acceleration until I know my force, right? And so I have this implicit connection. And OpenFAST will solve that, even in the loose coupling sense. So later on, I'll explain which modules are implicit, which are explicit, but that's sort of key to its solve. Again, the current implicit loose coupling scheme is numerically stable, but sometimes requires a smaller than desired time step, particularly if you have beam dyne on. And that's what we're fixing in this new tight coupling solver coming in 5.0. If you want to see, sort of look under the hood of what the loose implicit scheme looks like, it basically follows this sequence here shown in the figure. So basically the idea is if I'm at time step n and I want to get to n+1, that's sort of what my goal is. So I know everything at n, I just want to get to n+1. Step one basically says I take all my inputs that I know and I extrapolate them out the next step. So here's my guess. I can look at my past history. If I know my previous n-1 and my current one, I can do linear, say, extrapolate out. OpenFAST actually allows both linear or quadratic extrapolation of inputs. So quadratic, 2 past time steps. So the first step is just guess out. I'll just follow where I think I'm going to be, extrapolate out. Then some of these models are very explicitly set up. So if I know one, I can calculate the next. So I do those for the ones that are explicit. The rest are implicit, where I say I can't really solve these guys without knowing these. And I basically set up a big Jacobian and try to solve that implicit problem through a Newton iteration scheme. That's step 3. So it's basically implicitly solving the input-output equations. Once I've done that, there's some of the modules that are still explicit, but depend on that implicit solution. That's step 4. And then basically at that point now, everything's been advanced to n+1. But I have realized that some of my inputs to make that happen were extrapolated. But now I've calculated new inputs because I basically advanced all the modules. And so basically I can say I can take my outputs and use those to inform my inputs. And I can do what we call a correction. That's step 5. So I can basically go back and do it again. That's a sort of implicit loose coupling scheme. I can do it, take a correction and try again. Usually there's balance there between, if your time step is small enough, you don't need to add a correction, but if your time step's quite big, correction can be useful. So usually you're trying to balance the correction steps and the time step. And I would say most of our models don't have corrections. Some of the offshore models that are pretty complicated with lots of interactions, we usually go up to 1 correction. Almost never have to do 2 corrections. These are things you can play with and solve to try to optimize your performance. Big part of the input-output coupling is a spatial mesh-to-mesh mapping. For example, this is showing, say, a hydrodynamic mesh where I have my spar and I have a bunch of beam elements, say, to represent that spar structurally. Hydrodynamically, I have my hydrodynamic force, but it's distributed. The mesh mapping allows us to couple those things together, even it's not just one point now, it's a full, say, line mesh of interactions. And so every module that has this sort of spatial boundary to it, we've set up a mesh data structure. And that mesh consists of basically three things. There's, what are my elements of that mesh? If it's, rigid bodies or point forces, it could be a point mesh. If it's like a line, like a beam element, or distributed, force per unit length, that would be a line element. So every node or element basically has some sort of reference, position, orientation, say, of that reference. Position also has fields on it. So what are my inputs and my outputs on that mesh? So that could be, that point has motion, position, velocity, acceleration, say. Maybe that point has forces on it. Maybe it's some other scalar quantity like temperature or something. I'm not sure. But every mesh sort of has this sort of set of what we call fields. Really the inputs or outputs that fit on that mesh. And our mesh to mesh mapping is all sort of in the background. So every module that uses the mesh, you basically define what it looks like. So hydrodynamically, I say, here's my discretization of my hydrodynamic mesh. Structurally, here's my discretization, say my beam elements. And one thing you'll kind of notice when you're on fast is they don't have to be the same. Like my nodes don't have to line up. You almost have to do the work twice because you have to discretize, both hydro and structure. What's happening in the background is this mesh mapping makes that connection happen. So you may ask, well, why do I have to do it twice? And it really is because of this. And it is both maybe a little confusing, but it's also very powerful because basically you can say, well, hydrodynamically, I can define my mesh where I think it makes sense hydrodynamically. So usually if you think about hydrodynamics, exponential decrease of velocity with depth. So I want a lot of discretization near the free surface and really coarse down deep. Structurally, if that's just a simple beam, maybe it's uniform distribution. Aerodynamically, it's usually also something like that, like very, very quick change of stiffness near the root. So I want fine discretization. The rest of it's pretty, straightforward. Aerodynamically, a lot of things happen near the tip, so I want to find discretization there. So like the meshes are mismatched. So this allows us to do that. So again, every module defines its own mesh. And the mesh mapping works in the background to sort of make sure that data can be shared. So how does it work? Basically, I won't go through all the math. There's a nice paper on that if you want to see it. But it does support extremely disparate meshes. So if you want to say, well, I have this jacket model hydrodynamically, I want to model all the members, but structurally, I just want to say, well, it's one beam. I just want to get the first mode, say, of that system. You could map that thing together, and it works. So extremely disparate meshes. You can do points to points, lines to lines. You can also mesh lines to points and points to lines. We haven't gone to surfaces. We haven't needed to do that yet. That could come in the future. It does support large motions. So again, the large rotor, of course, rotation is certainly one. So the structural mesh is moving around, and the aerodynamic mesh will move with that large motion, large deformation as well. In terms of mapping guidelines, so the load transfer. And so if I have distributed load, on one mesh that I want to map to the structural mesh, that's a different discretization. First of all, if the nodes are exactly the same, so 1-to-1, the data transfer is 1-to-1, so there's nothing lost. But if it's a very disparate mesh, it'll make sure that the total load and the total moment are still, total force, total moment are still correct when you get that mapping. Basically conjugate for motion. So if I have an offset, say in this, beam structure representing that jacket, if that one beam is moving, basically everything, assumes that farther away, it's basically rigid connection to that beam. So it maintains rigid body motion, even if for basically any offset to the mesh. So hopefully that's clear. This is showing one example. I wanted to make an animation, but it might work, so I kept it this one. But just picture it as two different modules. So the module one there in the middle column is like, it's say the structural model. It's saying I want to input loads, aerodynamic loads, say, and I'll give you motions back. And it's just a point. So I've taken my whole, say, blade, and I'll just say it's 1 point. That's rigid. Aerodynamically, I've distributed that aerodynamic load across the blade, say in 5 points, and I want to know motion of those 5 points, and I'll give you loads back of those 5 points. So that's the idea. And so the way this mesh mapping will work is say my structural model displaces 2 meters in X and it rotates a bit. So there's the motion mapping that will say, okay, we'll take all those 5 points and translate them 2 meters, then we'll rotate the whole thing as rigid body. So like the blade is spinning. And that's what the aerodynamic module will see is not just a single point, it will see all 5 points moving. Now the aerodynamic model will do its thing and it will calculate, say, some force distribution across that blade. Then it needs to get passed back to the structure. So it basically integrates those forces up, and the total force of the blade will be the integration of all that. And because some of these nodes were offset from the 1 point I do have, that distribution will also create a big moment when it shows red. So the mesh mapping basically supports that sort of interaction. So again, if you do a disparate meshes, that's what's going on in the background of OpenFAST. Self-explanatory. Now linearization. Again, really what you look at in the module, there's nonlinear equations of motion, say for constraints. I'm showing, say, simple example there with no discrete time states. But that's my system, say a module has. Tries it basically, the linearization is basically you say, I have some operating point I want to perturb about. So say there's my input with the UOP, that's my operating point input. I also have an operating point for my states and my output, but I basically linearization is basically some perturbation relative to that operating point. And I can basically take that nonlinear system shown on the top and represent it as an ABCD state space model. And where the A and the B and the C and D are all basically Jacobians of states and the constraints and the inputs relative to the states, constraints, states, constraints, inputs. So I'm showing, say, what the A matrix would look like there. If you have no constraints, it's just, the D of that big function X with respect to the state. That's what A would be. If you do have constraints, there's a little algebraic manipulation there to basically eliminate that constraint. Once it's linearized, constraints are really easy to remove because they're linear. So that's showing what A would look like in that case. This all happens in the background again. So basically, all 10 modules shown there can be linearized. So whatever equations are inside that are non-linear, all 10 of those can basically output what their ABCD looks like based on their inputs, their states, and their outputs. Really powerful. And then I guess the key with linearization, of course, though, is the model is underlying, it's non-linear. And so this linear model is only valid for like small perturbations about that operating point. If you linearize the model at 8 meters a second, probably not very valid at 18 meters a second. Models look so different at that point. So that's it. I think the hardest part for people to understand with these linear models is that, well, why can't I use it everywhere? It's because it only works for perturbation because the underlying model is non-linear. So what do we do? So every module is to show an example. I say every module, all 7 of those, I say, well, here's its sort of state space representation. And OpenFAST can generate those things at the module level. Glue code also sets up its based linear system. So the glue code linearization is fully analytical and again automated. So it represents coupling between the inputs and the outputs that it sets. And so that's done linearization. Once I know all that, it's basically some algebraic manipulation to combine it all together. And so I can then represent the global system ABC state space model in terms of basically the full system now. So it's, a couple of things to point out there. The D matrix, if you're familiar with state space, that really highlights all this coupling, including the role of direct feed through from one module to the next. And say for elastidine, elastidine will have the mass, stiffness, and damping of just the elastidine model. But the full system version of A will not just have the structural information, it will also have the full aerodynamic interaction. And so now say my damping will have the aerodynamic damping built in. As Manuel said, that can also lead to instabilities if you're not careful, if you're good on your design. Aerodynamic stiffness would be in the matrix, and the full system has that full effect in it. So A nice thing about linearization is you can look at it in individuals modules linearized form if you just want to understand what that module is doing, or you can look at the couple interaction through a state space formulation. So really powerful capability we're able to keep with our linearization framework. Just showing how that looks like in terms of the inputs. I think maybe one thing that confuses people a lot. So you can say, here's what my on the left is basically the nonlinear time domain solution. So again, I have these big functions, my continuous time differential equations, my constraint equations, output equations. So every module has their own set with a big set of algebraic coupling equations U there. In the time domain, you're basically doing the interaction, giving input, solve for output. In linear sense, basically, we do a perturbation in every input option. So what we call this U plus delta U plus. That's like I can perturb any sort of input in my model, and then the state space model looks like that. So, well, what does that perturbation input look like to its perturbation of an output? So just trying to paint the picture of what that linearization looks like. A couple of final things in the visual in terms of what the modulation framework does. One is again generation of VTK files. So you can output a stick figure representation or a full surface geometry representation. And again, you can use ParaView to look at that. So in OpenFAST, you basically just output. You say, well, what do you want to output? Stick figure or full system? Do you want to do it in every time step? You just want to know what the initial configuration looks like. And you basically generate VTK files, then you port that into ParaView to visualize. Another capability of OpenFAST is checkpoint restart. That just means basically any point in time, it can basically dump all its data to a checkpoint file, and then you can basically restart from that checkpoint time in the future. That's usually not that important if you're just running OpenFAST by itself, but if you're coupling to say large eddy simulation, where those simulations may take a week, if you have a hiccup on your computer, you lose power or something, checkpoint allows you to sort of start where you left off. So again, not too useful just for OpenFAST, but really useful for the company to type LE simulations. And then finally, I think from this section, again, open source, we have this Apache 2.0 license. This is very basically just indemnifies NREL. So if you run OpenFAST and it doesn't work or you get the wrong answer, you can't sue us for that. You use at your own risk sort of level. It's also completely free in the sense that if you want to take OpenFAST and change something and give it away yourself, that's open for that too. So if you're familiar with these open source licenses, GPL is the other popular one. GPL is much more like if you make your code GPL, it sort of propagates. Everything is GPL. Apache is like, do whatever you want with it. You just can't blame us if something goes wrong. So yeah, people have used this to advantage. A lot of commercial codes will take pieces of OpenFAST and then resell it as a package. Our Apache license allows them to do that. I'll pause again there on the framework. Any questions on that set of topics? Please. It does. It works with everything in the ecosystem. So that may be a case where it may be useful. If you have a really big farm and the simulations are taking a while, it could be used for that. It really again, it doesn't allow you, it allows you to restart from where, at the last checkpoint. It doesn't allow you to change the simulation. You can't run it and say, well, I want to now do something else. It's not set up for that. It's really set up to say, keep going. That makes sense. Anything else? Yeah. Well, it is. I mean, it depends how you're asking that question. So it is linear, of course. So it's, I guess, first order accurate, but right, exactly. Right, you're getting that first order term. You're not getting the quadratic terms in it. Exactly. I mean, if you're asking more about second, you can say F equals MA is second order because there's two derivatives on X or so that is in there. So we represent that in the state space form where the state, so if I have, that mass spring damper system, I have my displacement, velocity, accelerations. The states again are displacement, velocity. So my X is those two things. So it has that, second order form because there's two derivatives. So I have, X dot's a function of X in that case, rather than X double dot. But yeah, the model is only first order accurate in terms of it's just that first term of Taylor series.
Finite differences. Central finite differences.
I see what you're saying, yes.
Yeah, it is really what we're talking about.
Yes, that's another way you can think of it. So, so is it just to clarify Manuel's point? So some of the modules of OpenFAST are full analytical Jacobians, and the glue code of OpenFAST is full analytical. So it is completely accurate, no loss of accuracy. Some of the modules are more historic in nature and not easily written and analytical Jacobian, so we do a finite difference to get them. And depends on how the module is implemented. Most of them use a central difference perturbation, where we do a positive perturbation, negative perturbation divided by twice the perturbation to calculate the slope. So it is, yeah, it's like a second order accurate. First, I would say that it's better than Euler, one perturbation. So yeah. Yeah, I'll get to that in this next section when I talk about each module. Yeah, so exactly. So if you're not familiar with that question, the blades you can choose structurally to do that either elastidine or beam dyne. You can't do both. You can't say I want one blade elastidine and one beam dyne. So you have to choose, but you can do it either way. And beam dyne tends to be more higher fidelity, more accurate, a little harder to set up because there's a lot more data needs a lot more parameters to set up. And definitely slower, although tight coupling will fix the slow part of that. So we'll get into that more as we get to the next section. Yeah. Maybe
Which type of meshes?
meshes in what kind of
Like example meshes.
Our models are basically all like we don't have, there's no finite element mesh or anything like that. Even the aerodynamics or the fluid or the hydrodynamics, we don't have mesh per se in the sense
right.
Finite software. But generally we use meshes to relate the relationship between points and lines and
Yeah, so structurally it's always beams. We never get to the solids of the shells. As I mentioned earlier, like you typically use the solid shells maybe as a pre-processing engine to get to the beam, or as a post-processing engine after the beam. But in terms of OpenFAST, it's a beam. Aerodynamically, also, it's always a line, like an actuator line. You never say I discretize the surface of my blade. If you want to do that, that's the CFD method, and you have to go to NAWEA for that. But I think the other mesh we have, say, is Olaf has a mesh. We discretize the wake, say, with a mesh, and I'll talk briefly about that. But yeah, FastFarm has a mesh as well. Usually it's either points or lines. That's the case. Anyone else?
No, but
Visualize the wave interaction. Wave interaction, is that what you asked? Yeah, I would say, well, right now you can definitely visualize the wave, the free surface. Like if you have regular or irregular or some spreading wave, like you can visualize the wave elevation coming in. Internally, it is calculating what the impact of that wave is, like the radiation wave. Like it's calculating the effect of the radiation, but you can't currently visualize the radiator wave. So you can only visualize what's coming in, not what's going out, if that makes sense. So it shortcuts that solve, doesn't have to track all the particles. So you can definitely visualize the wave elevation coming in. You can visualize the turbulent field, say, coming in, UVW of all the components coming in. You can visualize that. I think I'll do one more section before the break. Then we'll have lunch. So this section will be about the core modules tied to the turbine. And then I have another section more on all the offshore things. But we'll split those out into two. We'll see how far we get. But we'll stop at 12. So first of all, on the turbine, just kind of talk about each module. Again, you asked about last time versus beam dyne, since your slides. Elastodyne, if you know old codes like Flex, the old version of Bladed was like this. I think, was it D-Flex at Orsted, maybe? Very similar. Yeah, Elastodyne is kind of based on that older form, although still quite powerful, I would say. Elastodyne is fixed configuration, so it's, horizontal axis, 2 or 3 blades. Actually, you got an ability to do end blades now, isn't it? So that slide is wrong. Sorry about that. The rotor can be upwind or downwind, rigid or teetering hub. You can have, if you have tail fins or something, you can have that. And then, really is just a blade, drivetrain, nacelle, single mono tower. That mono tower is built on a 6-off motion body. We take advantage of that for lots of things. But that really is Elastodyne. Like it's not a flexible open source multi-body formulation. It's fixed configuration to that. It has up to 24. We'll go, although you can now dynamically allocate blades, but normally for 3 blade it'd be 24. So you have 3 degrees of freedom per blade, 4 degrees of freedom for the tower, and everything else is basically rigid bodies in the system. It is fixed configuration. You show like modulation sense again what it looks like. It's the states, of course, displacements, velocities, parameters, all your geometry, mass, inertia, stiffness, structural damping, say gravity is a parameter there. Inputs, all your forces coming in, aerodynamic, hydrodynamic control system. Outputs are the motions and loads coming out. So a little bit more information. It uses a relative degree of freedom sense. So if you imagine, first thing we do is we move the floating platform 6-off motion. Tower deflection is basically relative to that. So if I pitched 10 degrees, my tower deflection would be relative to that. Blade and tower deflections use some small angle approximations in them, showing what that looks like. We do have this, what we call correction for orthogonality. So if I have combination, say a flap and an edge, linear sense, that's what the transformation will look like between global and local. Cosine becomes 1, sine becomes beta. So that's what a linear version look like. We actually take it one step beyond that. We basically say what's the closest orthogonal matrix to that, and that's the equation we use in OpenFAST. So whereas in small angles maybe get you to 5 degrees, this gets you maybe to 20 degrees before it blows up and still loses lots of accuracy. But that's what's in there for the blades and the towers. You have to be careful. You can't go too far on deflection without that. The platform rotations used to have the same transformations, so roll, pitch, and yaw used to be that way as well, where we use that transformation. Coming out now in 4, we've introduced the full Tate, Bryan angle sequence. So we do a yaw, pitch, roll convention now. That is coming in with 4 blade. That allows us to do like large yaw motion, say floater. All other degrees of freedom in the model are completely large, large motion. So surge, you can surge as much as you want, azimuth angle or yaw angle. You can yaw as much as you want. It's not, there's no small angle assumptions there. So a lot of people think of Elastodyne, well, there's some modal elements in there, so it's linear. It's definitely not linear. There's lots of nonlinear terms in there. And internally, if you're not using tight coupling, you can either use like an RP4, linear cut integrator. You can use like an Adams bash for the linear corrector scheme internally to solve its states. Now the beam model, I think that's what the limit of this model is, other than its fixed configuration. So it is using Euler-Bernoulli beams. I mean, there's no shear correction in there. Usually that's not too important for high aspect ratio models. It is straight and assumed to be isotropic material. So no like bend twist coupling term in there. It's bending only, so we don't have torsion. That's probably the biggest limit of this model. Although I read, actually, I'm playing out. I now have an idea how to get torsion in there. So I want to talk to you about that at some points. But Oersted took this model one step further. So I love looking at that. Anyways, it's bending only right now. And so yeah, if your blade has important torsion effects, that's not great for you. Bending only uses, so in terms of these the mode shapes, it's actually not using, it's not really a modal method. It's called the Rayleigh-Ritz method, where it sets up some nonlinear equations of motion, and you give it shape functions for its solve. But because we have so few degrees of freedom in that model, unless you give it the mode shapes, it's kind of like you can get an answer. Like if I just want to say, I don't know mode shape my blade, I'll just use a quadratic, x squared. That's good. It'll work. Like it'll give you an answer. It may not be the best answer, but it's not going to give you a terrible answer. But if you give it good mode shapes as input, as shape functions, it'll give you a good answer. So we usually recommend using mode shapes as input. And there is some nonlinear terms in there. For example, radial shortening effect. As my blade bends upward, the tip is going to get closer to the root, less it's stretched. We don't have stretching. That term, that radial shortening, is really important for like centrifugal stiffening of the blade. That term is in there, even though we are using, a mode shape method. So that there's like a correction there for nonlinear effects. Also, things like gyroscopic terms are nonlinear. Those are all those terms are also in there as well. The big thing is, unless the blade is straight and doesn't have a lot of torsion, this model's great. If it does have, curved blade or has some torsion effect, not a great model. So hopefully that answers your question. That's all I have. Again, without going into all the details last time. Beam dyne, if you want to take that next level above, beam dyne has full 6x6 mass and stiffness matrices with any coupling you want. So if you want composite coupling, say between bending and torsion, you could have that in beam dyne. It is 6x6, so in addition to bending, it has shear, it has torsion, it has stretching. It's all in there. Also, the blades can be initially curved. So the elastidine requires the blade to be initially straight. This can be, you can define some curved axis where the beam properties follow the curve, and all that coupling associated with curvature is in the solution as well. It uses this geometrically exact beam formulation, so it's a nonlinear finite element beam model, which is basically the be-all end-all of beam theory. You can't go beyond that. It'd still be a beam. And so, mean that geometric. So you can bet like there's no geometric limitation in the model. So talk about 20 degrees, say for OpenFAST beam. This you can bend the thing in a circle. It's still there's no geometrical limitation. There's no limitation there. You may start violating linear elasticity theory, but that's a different problem. Uses the Legendre spectral finite element, meaning instead of doing like an H finite where you say, well, the more elements I throw, the better solution. You keep it with one element and just say how many nodes I want, and uses a higher order polynomials or what's called Legendre spectral elements for its formulation. So you always basically do the blade with one element, and just the accuracy is dictated by how many nodes you put in that element. Allows you to basically do what we call exponential convergence. So the fewer degrees of freedom, you can get a more accurate solution. Whereas a more H refinement requires a lot more degrees of freedom for the same level of accuracy. Otherwise, in terms of modulation framework, looks very similar to acetylene. Displacement velocities, aerodynamic loads coming in. I think the trick in terms of how we couple that to elastidine is we say, well, the root motion is also coming in. So that what's the hub doing? My blade's going to follow that. So the root motion's coming in. And in terms of elastidine to solve its response, is coupling elastidine to beam dyne. The rest of the turbines, beam dyne is only a blade. Elastidine needs to know what the reaction load of the root is to solve its system equation. So that's coming as an output, which would be an input to elastidine. that answer your question, or do you still have more questions? Please. Correct. Last that I can't handle the pre-bend of the blades. Exactly. If your blade does have some pre-bend, likely torsion is going to be important now. If you do an edge vice force on a pre-bent blade, you got to get a torsion. Like elastomeric will kinematically calculate that moment, but it can't twist the blade. There's no torsional freedom there. So yeah, so if you have sort of pre-bend geometries, beam dyne is your option. Well, elastodine's screaming fast, no problem. Beam dyne, again, historically was really slow because, well, usually, yeah, so internally it has this generalized alpha solvent. So we can take big steps, but when you couple it to elastodine, complicates the problem and it drives the time step down. And so, yeah, historically, beam dyne, an really accurate beam dyne model, say 10-minute simulation, was taking a few hours. Depends on how many nodes you throw in the model. If you want 50 nodes, maybe it's the whole day to run that. But with tight coupling, we brought that back up. So usually we're talking about an order of magnitude of 10 to 100 times faster than it was before. Same model. So if it was taking 24 hours, we can now do it in 20 minutes or something.
Slow down when you're on
It could slow down AMR wind if your beam dyne was resolved enough. And actually, that has led to some things. That was one of the reasons we go to tight coupling, but also we just want to make it faster. But two cases with AMR wind, it was the bottleneck, which was like that doesn't make sense. So, anyways, again, that is fixed in the 5.0 branch, and if you want to start playing with that, you could access that through the GitHub. So it does work already for the land-based turbine. We're just finalizing the approach for the floating case. Yeah.
We can take time.
So yeah, I would say right now, sort of our baseline model we run is the IEA 15 megawatt, which I think we use a 10 node beam element for that. So it's like pretty accurate. And with that, with tight coupling, running 10-minute simulations in 20 minutes now. So it's 2 times slower than real time. If you coarsen up that beam dyne model, and you can probably run it real time, but you'll lose some accuracy. Well, if it has curvature or twist, definitely. So if it is like bending only, that's the only thing that really matters. Last then will definitely be faster. But you can't get torsion, you can't get curvature out of it. So, yep. Yeah. Aerodyne is our aerodynamics module. There's several sort of submodels there. So one, of course, is the induction calculation. And right now there's basically 3 main options in Aerodyne for induction. One is sort of classic blade out momentum theory. If you study wind energy, I'm sure you know what that is. I won't go into all the details, but you basically, discretize the blade into a bunch of annuluses, and you do a momentum balance in each annulus. We're definitely doing that. Solve basically, in that balance, it's basically an algebraic constraint. It says what's the induction factor, what's the inflow angle. Based on induction, it's doing that solve. The next form of that is what we call dynamic wake model. It basically does the BEM solution, but adds a time filter to it. So, for example, shown in this Burton et al. Paper, if I say do a rapid pitch event, from one state, quick pitch, say to the next state, the BEM solution would just say, well, it's 2 states, and I'll just step from one to the next. In reality, what you see with the measurements is that you get some overshoot and then some reaction back, and so that's basically like a filter. And so we introduced that dynamic wake to basically a time filter on BEM, and that captures that effect of that overshoot and reaction back. The final approach is our free vortex wake model. Manuel got his PhD on that topic. And so that's what we call OLAF. I have a one slide next to talk about what that is at a high level. BEM solution, of course, has tip and Hobloff corrections, speed wake corrections, and a Glauert correction for high thrust. And actually, there's some recent updates there too. If you're at Torque, Manuel presented on our recent updates to BEM, which I think I'll show at the final end of this presentation. Then in terms of the next sort of model, it's not just the induction, but also what happens aerodynamically locally at the airfoil. Again, we're not doing a discretization of the blade. We're doing a lift and drag pullers. And so we use this actuarial line approach, and that actuarial line can be quasi-steady, meaning, based on the angle of attack, I know what my lift and my drag are directly, or you can introduce these unsteady airfoil dynamics options. And if we're talking sort of like, low angle of attack, linear region, Theodorson theory applies. And that's in these models directly. And if you go to very, dynamically transition past stall, these deep stall aerodynamic models, and not deep stall, these unsteady airflow dynamics models like Bettel-Fleischmann or Hansen Gauna Hack, is that right? HDM models. What's that? That's it. Sorry. Take over. See, and there's different models. I think we have currently 8 different unsteady air models in OpenFAST, so you can choose which ones you want to use. Our go-to model these days, I would say, is UA Mod 4, which is the HMM 4-state model. That's with quite a few parameters. It can do a whole lot, and also fully linearizable, which is really nice. But we also have the original, classic Bettel-Fleischmann model if you want the 22-state form of that in discrete time. It works on the lift, drag, and the pitching moment. If you're doing underwater turbines, you also get buoyancy, added mass, and fluid inertia, at least the added mass and the fluid inertia coming in 5.0. And then it's on 2D or 3D airfoil data, which, you use a tool like airfoil prep, say, to extract from. Turbine in its modular form looks like I don't have OLAF in there, but continuous states would be like this filter of induction and debend for the states in the HGM model. Discrete states would be the Bettel-Fleischmann states. Constraints, of course, are like induction and bend. Things coming in, fields are coming out. But maybe one more thing there. So when you run the driver of Aerodyne by itself, this is what the driver basically has to specify. So you need, the driver, standalone drivers, basically you define what the inputs are that normally you would get to the coupling. So when you define the driver for Aerodyne, you get to say, well, here's what my motion of my turbine is going to do. Here's what the wind is going to be. And that's what's specified in the driver to get Aerodyne to run. And all these sort of make sense once you sort of see it in the modular context. So why do I have to specify that? Because that's what the inputs need to be. One more slide on Aerodyne. Again, if you don't want BEM, you can use OLAF. That's this free vortex wake formulation. We use a hybrid lattice filament approach where we basically near wake, we do a full lattice, you're doing the trailing and the shed vorticity, and you track that at some point. At some point, you can roll that up into just the filament, basically like a tip vortex and a root vortex that extend for longer periods of time. So you can choose how you want to discretize. You ask about discretization. So you can choose how much you want near wake, how much you want far wake. Obviously, it's using the Biot-Savart law for computing the induced velocity from the vorticity. There's quite a few regularization methods in there, to handle that vortex. This does have an open NP parallelization because that Biot-Savart calculation and tracking all the vorticity can be fairly slow. So we do an NP parallelization of that. It is open NP, so you still need it's only one node. You can't do it across multiple nodes, but you have a lot of cores. You can use that capability. So the nice thing about this is also works not just for single horizontal axis, it works for multi-rotor systems and vertical axis. We use that. I won't talk about that too much today, but later this week at NAWEA, I'll talk about our new work to do multi-rotor simulations, and that's really taking advantage of Olaf underlying capability. Another model of Aerodyne, of course, is how we deal with the cell and the tower. Quite simple things there. For the tower, you define, you either do like a potential flow solution around the tower to get the effect of the tower on the inflow. Basically distorts the wind. It was a potential flow model. If you're downwind, we use this tower shuttle model. Basically tracks that deficit. Not really I feel other things like vortex shedding. That's a bit beyond what Aerodyne can do currently. So hopefully in the future we can do that. There's also some tail fin options, which I won't really talk about. Nathan, any questions on Aerodyne? Does that make sense? See anything? Inflow wind is a very simple model. Basically, allows you to use different formats for inflow. And if you just want to say I want to run 8 meters a second, and I don't, it's a steady uniform, you just type that in the file. If you want to do, various deterministic cases like the best cases from IEC, ECD or EDC or whatever, there's scripts like IEC Win that can generate the info file for you, or you can just type it up yourself. But you can also do full field turbulence, again, using TurpSim or the mod model. I won't really talk about those things there. Just inflow one basically just says, okay, here's the file, use it directly. One thing it is doing internally, these sort of TurpSim or mod formats, is it does this Taylor's frozen turbulence assumption, because TurpSim basically defines a 2D plane as a function of time. So across that 2D plane, there's UVW spread across the plane. But to create the 3D volume we need for OpenFAST, we basically take that plane, we propagate it through at the mean velocity of the wind. Bond model is very similar. It's a 3D frozen box that we just push through time or space. Basically, the X component is type B. So that is what we're doing. So pushing those planes or wires through the turbine. You don't like any of those things, there's also user-defined option where you can say, I just want to, say what my wind is at a given point, and you can write your function like that. I write it in modular sense of saying, well, positions will come in and the wind at that position will come out. It's not really how it's coded up. As of I think 3.4 and newer, this is all done through pointers in the code. So basically, it sets up a data structure that the modules will call and say, well, give me the wind. So now Aerodyne can basically call inflow wind directly and access that. That just makes the code a lot more efficient than we had it before. I think this is my last slide for this section on turbines. Servodyne, also, pretty simple internally. There's some built-in options, but not too many. Mostly Servodyne's an option to interface your own user-defined controller. Again, I think saying, controls tend to be the most secretive part of the wind industry, and so we set up Servodyne to support that. So again, very simple options, built-in options, with some links to some four-channel routines if you just want to code it that way. The more popular things to do are the bladed style dynamic link library. So if you have a controller in bladed format, you can just connect to it directly. Our Roscoe baseline controller is written in that format. We also have a MATLAB Simulink interface for OpenFAST. So basically, OpenFAST now becomes a block in your simulate model. Its output could be anything that OpenFAST knows about in outputs, and the inputs are basically all the control function inputs model. We used to support a LabVIEW interface. That's not yet an OpenFAST, but that's useful if you're doing hardware loop simulation. Servodyne is, I guess you just listed what it could do there. Torque, yaw, brakes. Beyond that, those are all standard things. You have a few things that are sort of non-standard. One is you can control cables or tendons in the model. Like if you have a mooring line, you want to control, winch up the cable. There's interfaces for controlling that. There's also a lot of aerodynamic flow control options. If you want to, control your trailing edge actuator or something, Servodyne has interfaces for that. And then quite a few structural control options as well. This is pretty powerful. So basically anywhere in the system, you can place as many structural controllers as you want. I mean, mass dampers, tuned liquid column dampers, also just user-defined point load time histories. Basically, dynamically allocate as many of these as you want, and you can put them in the blades, the cell, tower, or substructure. And so, this really opens up as many degrees of freedom as you want to add. TMDs, TLCDs, you can basically do that in this module. But that's basically also faults. There's a few simple cases there. If your pitch controller is running happily, through the server amplifier, you can say, well, I want to override that pitch and ignore the controller and do this instead. You often use that for fault cases quite. Or I want to turn off the generator. At some point, you can do that through Servodyne. That's again a pause there. Any questions on turbine capability? The next section's on offshore. Probably do that after at 3 o'clock. But questions on turbines? Yeah. Yes. So the type coupling. I think I explained it later, but type coupling only really affects beamdyne, elastodyne, and subdyne. I haven't talked about subdyne yet, but it takes the integration out of those modules and puts it to Blueco level. There is some blending of that with the overall implicit boost coupling solve. I went through all the details that we last year, but it doesn't change. It doesn't really change influence at all. There's no effect there. So all the user-defined functions, Servodyne, wind, or customization of code will work for all that stuff. Yes. So that's a little bit different than user-defined wind because that actually has an aerodynamic interaction to it. So that's like almost so when we run CFD like AMR wind, we actually have, it's not just inflow wind, we don't use it all. But we start using Aerodyne. Aerodyne is still using like the actuator line, it's calculated lift and drag, perhaps with the HGM or the better sleep spin model running there. So the force is effectively calculated by Aerodyne. Go to the CFD solve, say, that's a body force now in the fluid, and then Aerodyne gets back the wind from the CFD solve. But it's not like the inflow wind, the ambient wind. It's more like the disturbed wind from including the induction. Any other questions? Yeah. Inflow wind does nothing other than Taylor's frozen turbulence. If you're talking about like preprocessors like TerpSim or the bond model, those are internally periodic. So like a TerpSim is using inverse Fourier transform, and so it's naturally periodic based on the length of time you've set up stochasticity. And Influent can take advantage of that, so it can say, well, if it is a periodic file, 10 minutes long, say, once it hits 10 minutes, it can circle back and start again because it's periodic. And Influent knows that. As long as the file is marked as a periodic file, it will know that and recirculate it through. Influent is doing that. As long as in TerpSim or the Mon model, you mark it as a periodic file. To do that, it has to output a full period. TerpSim allows you to actually run you know, I say I want to run 720 seconds, but only output 600. You can do that, and then it's not periodic anymore. So as long as you run terpsim and say I want to output the full thing, then it is periodic, and inflow will take advantage of that. Waves is exactly the same. So we'll talk about waves next, but yeah, waves can also waves. I think we always just say we don't have the option like terpsim has where we cut it short. Like it is periodic. So if you say I have 1 hour C state and you want to run for 2 hours, you'll get, you know, you can repeat it twice. Now, usually you're doing one or the other, right? You say maybe my wind's periodic and I'll do a 1 hour C state, or do the opposite. Like if both wind and waves are periodic, then you know what's the point around the second period? Yeah, you can mix and match them that way.
That direction is sensitive, that you put direction is sensitive and your speed. So I want to know how to achieve similar functions in terms of I mean, in NAWEA, in profile, we only can set a fixed direction for moment. And in the user profile, we can only set direction, different wind direction in different way. But in a specific case, we can only have a fixed direction to generate different directions.
Yeah, this kind of gets back to you know the frozen turbulence assumption of inflow wind is that, you know, to create a volume, we have 3D plus time. Go back a couple slides. It uses this Taylor's assumption, so it needs to propagate that box through. That really only works if it's a fixed direction. Like I can't say, you know, 20 seconds in, my wind direction changes, it'll propagate some other wind. Like it physically would be mismatched. And terpsim also is like, you know, well, both terpsim and the Mon model are like stationary. Like we assume we're in some stationary stochastic process. So there's a given spectrum, there's a given profile, and I'll just solve it in that case. But if I want to go, say, from 8 meters a second to 20 meters a second, we say, well, that's two separate stationary events. So I'll run one at 8, one at 20. Likewise, directions. Like if I'm saying I'm going to run at 10 degrees direction, or I want to run at 30 degrees, like I typically do that in two separate simulations, not one. Yeah, the IEC tends to separate them out that way, where we say turbulence is done stationary, and gust cases like the EDC event, extreme direction change event, we treat deterministically. We say here's a time series profile. You know, it's like what's shown there. The plot, like uniform wind is just like, you know, there's no turbulence there, but I can change the direction that really easily. Okay, so yeah, that's how the IEC lays it out. That's how we kind of follow here at OpenFAST. Is the turbulence is that fixed direction. So if you want different directions, you just run different simulations. But you can do direction changes in the uniform files. Fast farm, if you ask about fast farm, but that's a little bit different because now you're doing the full wind farm. And if you fast farm allows you the high fidelity precursor inputs. So if I want to run LES for some case, that LES has a big direction change to it, you can build that into your fast farm solution. We don't yet have that capability drafting.
Change as long as the main direction is the main direction, you can still put it in 20 degrees. Kind of locally, you can have some cross flow.
Yeah, I mean, so normally in terpsim we define that with a profile. Like it doesn't have to be a shear profile. You can have a veer profile. So like, but it's still like, yeah, if you have a veer, it's still like propagating it in one direction. Doesn't, if that makes any sense. Just have to get that sort of Taylor's assumption. I try to draw it there in the graph. I take the planes, I march it uniformly through. I'm not, you know, planes aren't changing distance downstream. why don't we call it there? It is 12, and so I think we ended a good time. So we'll take an hour break. I don't know if there's any food out there. I think they said pay your own, so I'm not sure what that means, but I think there's restaurants nearby. So we'll come back at 1 o'clock, and we'll talk about try to get our hands dirty and play a bit more hands-on, and Amanda will lead that part. So, yeah, please.